Each picture is another revelation, and each will provide humankind with a perspective on the universe that we've never seen. Today addresses a thrilling new section in the investigation of our universe. This telescope is one of mankind's perfect designing accomplishments. The more profound you look, the less you comprehend, ought to be the saying of our cosmology, particularly in the presence of James Webb. The beginning of a new period in stargazing has started as the world gets its most memorable glance at the full capabilities of the James Webb Space Telescope. In a mission more than 2 decades in the making, NASA launched the most costly science test ever built, a $10 billion telescope that will endeavor to capture starlight from the first galaxies to be born in the searing cauldron of the Big Bang. Regardless of encountering various delays, the Webb telescope has finally delivered the goods. However, the latest pictures captured by the Webb telescope are sending shockwaves through established researchers as they challenge our whole understanding of galaxy structure. All of a sudden, we realize that we might need to revise all of the textbooks about the start of the universe. Join us as we dive into Webb's most recent pictures, alluding to another universe at the edge of the cosmos. The generally accepted understanding of the universe is this: around 13.8 billion years ago, the Big Bang occurred. In its early seconds, the laws of physics as we comprehend them didn't apply. All that would eventually turn into matter burst forward in a matter of seconds. First particles like electrons, photons, and finally neutrons and protons, the building blocks of our atoms. Early seeds of stars, planets, and galaxies extended out from that earth-shattering moment, and space spread so that the universe became profoundly smooth. Perfection on a tremendous scale simply means that things inside the universe are somewhat equally dispersed. That is, if you were to put a cube around one part of the universe, it wouldn't be significantly denser than another random cube. On a smaller scale, like between galaxies or within a solar system, matter is uneven and filled with clumps. Physicists speculated that not long after the Big Bang, something many refer to as inflation happened. Essentially, what was once a small, packed-together universe expanded rapidly in a fraction of a second, and it continues to expand today. Inflation is part of the ongoing standard model of the universe, called the lambda cold dark matter (LCDM) model. In LCDM, the shape of the universe's direction looks somewhat like a funnel. It's wide at the top, expanding and spreading further out over time. That's one interpretation. However, others have emerged from the very pieces of data that researchers can actually observe and measure. That is observational astronomy. The reality is essential if researchers are to use models to make genuine predictions about the fate of our universe. Theoretical astronomy is about reasonable deductions that are shaped by the few things we truly do know beyond a shadow of a doubt. Something many refer to as the cosmic microwave background adds to a major piece of that observable data. The cosmic microwave background is composed of hints of radiation left over from an earlier stage of the universe. Radio telescopes can detect it and then translate the waves into a heat map picture of sorts. This picture shows us how the items in the universe were distributed around 400,000 years after the Big Bang, the earliest detectable snapshot of a universe without stars, planetary systems, and galaxies. Everything was closer together and nearly uniform, with the exception of small variations that became the matter-forming stars and galaxies. This picture serves as proof that the universe began packed together and has expanded to where it is today. We also know that the universe continues to expand and might measure to some degree how fast it's doing so. The cosmic microwave background also helps affirm that an earlier version of the universe was extremely hot, while our time is much colder. One way to test this model is by checking extremely far-off galaxies, comparable to looking back to the first few 100 million years after the Big Bang. The universe was simpler then, its evolution easier to study against predictions. Cosmologists initially tried to see the earliest structures of the universe using the Hubble Space Telescope in 1995. Over 10 days, Hubble captured 342 snapshots of a seemingly empty patch of space in the Large Magellanic Cloud. Cosmologists were bewildered by the overflow hiding in the inky dark. Hubble could see thousands of galaxies at various distances and evolutionary stages, extending back to much earlier times than anyone had expected. Hubble would go on to discover some extremely distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smudge that they dated to 400 million years after the Big Bang. That was surprisingly early for a galaxy, but it didn't cause serious concerns about the LCDM model, partly because the galaxy is small, just 1% of the Milky Way's mass, and partly because it remained isolated. However, when the James Webb Space Telescope came along, our understanding of the universe was thrown into chaos. NASA's $10 billion bet in full operation since the summer of 2022 has shown that galaxies formed much earlier after the Big Bang than researchers previously thought, and some of them are unexpectedly massive, completely overflowing with stars. These discoveries have thrown the entire academic community into a new reality in which their current theories no longer apply. The earliest and most significant galaxies seen by James Webb challenge the dominant thinking in cosmology. This is because other specialists estimate that each galaxy is observed from between 350 to 500 million years after the Big Bang, yet it estimates over 10 billion times the mass of our Sun. One of the galaxies, in fact, even appears to be larger than the Milky Way despite the fact that our own galaxy had billions of additional years to form and evolve. This implies that if the majority are correct, we are in strange territory, and this will require something very new about galaxy formation or a revision to cosmology. One of the most extreme possibilities is that the universe was growing faster in the first moments after the Big Bang than we predict, which could require new forces and particles. Since we believe we understand how gas, this particle-based matter, falls onto these early galaxies, and how star formation feeds back and prevents future gas from falling in, there's a limit to how quickly material can accumulate onto these objects. While certain physical conditions can momentarily push this limit, it should not be sustainable over long time scales. We typically see a limit of about 10% of gas converted into stars, but for galaxies to form so quickly and at such a size, they would also have to be converting nearly 100% of their available gas into stars. So, while a 100% conversion of gas into stars is technically at the edge of what is possible, it's still the case that this would require something to be fundamentally different from what we expect. Many people immediately argue that standard cosmology might be entirely wrong, and perhaps we should throw out the Big Bang as the explanation for the origin of our universe, too. They speculate on new laws of physics, like an earlier form of dark energy that existed in the early universe, or new physical anomalies, such as the universe being born with very large black holes, or new exotic types of matter, like a primordial particle that decays into ordinary matter at relatively late astronomical times. While many individuals believe this explanation is completely outlandish, that's not true. Recall that even before the official launch of James Webb, various problems had emerged with our current standard model of cosmology. For instance, one problem is the nature of dark matter. One of the basic issues with the LCDM model is the concept of dark matter itself. Dark matter has not been directly observed. Its presence is inferred from gravitational impacts on visible matter and the cosmic microwave background. Despite extensive searches using various detection methods, including direct detection experiments and indirect galactic observations, the particle or particles that comprise dark matter remain unidentified. Another issue is dark energy and the cosmological constant. The inclusion of a cosmological constant, lambda, to explain the accelerated expansion of the universe is another contentious point, initially introduced by Einstein and later discarded. Lambda was revived after observational evidence suggested a speeding up universe in the late 1990s. The challenge lies in reconciling the tiny value of lambda, predicted by quantum field theory, with the observed energy density of dark energy, leading to what is known as the cosmological constant problem. Structure formation and simulations also present challenges. While the LCDM model successfully predicts the large-scale structure of the universe and the distribution of galaxies, discrepancies arise on smaller scales. Simulations of structure formation sometimes overpredict the number of small satellite galaxies around larger galaxies like the Milky Way. This missing satellite problem suggests that either our understanding of dark matter is fragmented, or the simulations need additional refinement, such as incorporating baryonic physics, normal matter, more accurately. For the cusp versus core problem, another issue within the LCDM framework is the cusp versus core problem in the density profiles of dark matter halos. Simulations tend to predict a cuspy central density profile for dark matter halos, while observations of dwarf galaxies and other structures suggest a more core-like profile. This discrepancy raises questions about the effects of baryonic feedback processes, such as supernovae and black hole formation, on dark matter distribution, which are not fully understood or incorporated in current simulations. The tension in Hubble constant measurements is another challenge. Recent measurements of the Hubble constant, describing the rate of expansion of the universe, have shown a persistent discrepancy between values obtained from local measurements using objects like Cepheid variables and those inferred from the cosmic microwave background by missions like the Planck satellite. This tension suggests possible flaws in our cosmological models, including LCDM, or the presence of systematic errors in measurements that have yet to be resolved. Beyond these specific challenges, the LCDM model also leaves unanswered some fundamental questions in cosmology. For example, it doesn't explain the nature of inflation, the epoch of rapid expansion. While the LCDM model is robust in many ways, it faces ongoing scrutiny and challenges from both observational data and theoretical anomalies. One of the major mysteries in current cosmology revolves around the nature of dark matter. This elusive substance, inferred from gravitational effects on visible matter and the cosmic microwave background, makes up about 85% of the total matter in the universe. Despite decades of research and numerous experiments focused on direct detection, the particle or particles that constitute dark matter remain unidentified. The quest to understand dark matter is not just about solving a fundamental riddle of physics. It also has profound implications for our understanding of galaxy formation and the large-scale structure of the universe. The discrepancy between simulated predictions and observational data on the distribution of dark matter halos, such as the cusp versus core problem, highlights the complexities involved. While simulations often predict cuspy halos at the centers of galaxies, observations suggest a more spread-out, core-like distribution, especially in smaller dwarf galaxies. Additionally, the missing satellite problem persists. Simulations tend to overpredict the number of small satellite galaxies around larger galaxies like the Milky Way. This discrepancy raises questions about the interplay between dark matter and baryonic matter, which includes ordinary matter such as stars, gas, and dust. Understanding how baryonic physics affects the formation and evolution of dark matter structures is crucial for refining our cosmological models. Another critical challenge comes from the measurements of the Hubble constant, which describes the rate of expansion of the universe. Recent observations have yielded conflicting results, with local measurements using objects like Cepheid variables suggesting a higher value compared to estimates derived from the cosmic microwave background. This tension points to potential flaws in our understanding of cosmological parameters or systematic errors in measurement techniques that need further investigation. In addition to these observational challenges, the theoretical framework of the LCDM model also faces uncertainties. The introduction of a cosmological constant, lambda, to explain the accelerated expansion of the universe presents a major issue. Quantum field theory predicts a much larger value for lambda than what observations suggest, highlighting our incomplete understanding of dark energy, the hypothetical energy that drives the universe's accelerated expansion. Furthermore, while the LCDM model has successfully predicted the large-scale structure of the universe, it encounters difficulties at smaller scales, such as accurately modeling galaxy formation and the distribution of dark matter. Understanding galaxy formation and evolution requires a nuanced approach that integrates both dark matter physics and the complex processes of star formation and feedback mechanisms. The James Webb Space Telescope, with its exceptional sensitivity and resolution, promises to shed new light on these processes by capturing detailed observations of early galaxies and their star-forming regions. The launch of the James Webb Space Telescope marks a major milestone in cosmic exploration. Building on the legacy of the Hubble Space Telescope, Webb's advanced capabilities allow astronomers to peer deeper into space and further back in time than ever before. By studying the faint light from distant galaxies, Webb will unravel the mysteries of galaxy formation and evolution during the universe's infancy. Early observations from Webb have already challenged existing theories of galaxy formation. The discovery of massive galaxies dating back to just a few 100 million years after the Big Bang suggests a much earlier onset of galaxy formation than previously thought. These discoveries raise crucial questions about the conditions in the early universe and the processes that facilitated rapid star formation in these ancient galaxies. Moreover, Webb's observations provide valuable insights into the evolution of galaxies over vast periods. By studying the diversity of galaxies at different stages, cosmologists can trace the development of their structures, arrangements, and star-forming activities. These observations will help refine models of galaxy evolution and improve our understanding of how galaxies like the Milky Way have evolved over billions of years. Beyond galaxy formation, Webb's observations also contribute to our understanding of the cosmic microwave background, CMB. By studying the faint luminosity of the Big Bang, astronomers can test early models of the universe and refine inflationary predictions. Webb's precise measurements of the CMB will provide crucial data to tighten cosmological parameters and deepen our understanding of the universe's origins and evolution. In summary, while the LCDM model has provided a solid framework for understanding the large-scale structure and evolution of the universe, ongoing observations and theoretical challenges compel scientists to refine and extend our cosmological models. The launch of the James Webb Space Telescope represents an extraordinary moment in space science, offering unprecedented opportunities to explore the universe with remarkable sensitivity and resolution. As Webb continues to unveil the hidden secrets of the cosmos, it promises to revolutionize our understanding of cosmic history and inspire new generations of astronomers to push the boundaries of human knowledge.